Hello, let's discuss the problem interference from the 2024 British Informatics Olympiad final. I'll put a link in the description to a playlist with solutions to the other three problems as well. So let's get right into it. Well, first of all, this is the problem. You can go ahead and read it if you'd like. I'll link the statement also in the description, but I will just walk you through it myself on a whiteboard. I'll walk you through the statement. So pause it here if you want to read it. But here is the problem. So in this problem, we have a graph with the nodes being stations and the edges being direct communication edges. And so there are two types of nodes and two types of edges. So the edges can be near or far edges. So in this diagram, I've used black edges as near edges and purple edges as far edges. And the problem asks you essentially to write a number on each one of these nodes so that certain constraints are satisfied. So the constraint, namely the constraints given by the edges. So the near edges, so the black ones, they require that the values at the endpoints are at most 1 apart. So in this case, 2 and 3 would be fine, 2 and 2 would be fine, but 2 and 4 would not be fine because they're more than 1 apart. And vice versa, 4 and 2 would not be fine, 3 and 2 would be fine. The purple edges have the opposite requirement. The far edges have to be far away, essentially. So that difference must be greater than 1. Absolute value of the difference must be greater than 1. So here, 2 and 4 is fine, but 2 and 3 is not, for example. So those are the constraints. But this problem would not always be solvable, right? If you have these nodes and two types, if you have any graph, if you can be given any graph with these two types of edges, well, obviously you're not allowed to have both a black edge and a purple edge between a pair of nodes, because then it would obviously be impossible because these constraints are opposites of each other. But also, even if that wasn't the case, you could still have an impossible case like this, where it can be shown that however you write numbers on these, this is impossible. Because you end up showing that these two values have to be equal. Since they're both close to this value, but far from this value, and this pair are close. So these two values have to be equal, but they have different constraints with one of them's close to and one of them's far from the same value. So this case is impossible. So we need something, we have an extra constraint in the problem that constrains the graph we're given further. So we're told that we have these special nodes called nodes in disrepair. And these nodes, which I've shown in red on this graph, constrain the graph further. So the constraints are that each cycle on this graph, let's say this one, each cycle in this graph must have at least one of these red nodes, one of these nodes in disrepair on that cycle, which, as you can see, is the case for this example. And two more constraints. So you cannot have two nodes in disrepair directly next to each other. So directly connected by any edge, black or purple. And also any node cannot be directly connected to two nodes in disrepair. Right? So these last two constraints can be combined to say that well, this one says that the distance between any pair of nodes in this repair can't be 1, so you can't have two nodes in this repair directly next to each other. And the second one says that the distance between two nodes in this repair cannot be 2. So it can't be 1 and it can't be 2. So we can combine these constraints by saying that the distance between two nodes in this repair must be at least 3, like this. So the distance is at least 3. So now we have this constraint, and also the constraint, like we said, that any cycle in the graph must have at least one node in this repair on it. So that's how the graph is constrained. This is a constraint on the input, not on your answer, because this is a constraint that describes the graph. So now, given this information, we're told that it's always possible, given a graph that follows, that satisfies these constraints, to write numbers on the nodes that satisfy the edges. And we're asked to do so. So that's the problem. That is the problem. So how do we do this? There's one more constraint that says, there's one more part of the problem that says that every number that you write on these nodes must be from 1 to 5. So 1, 2, 3, 4, or 5. So let's dive into the solution. So first of all, actually, this constraint here, that each number must be from 1 to 5, is actually helping rather than making the problem harder. This is essentially a hint, because the solution, the problem could be set without this constraint, but this is essentially a hint telling you to use the numbers from 1 to 5 only, because it's possible using only these. So what are we going to do? First of all, let's look at, well, pretty much the only key information we're given, which is all this business about the nodes in disrepair, right? So we're told that every cycle contains at least one node in disrepair, and the distance between every pair of nodes in disrepair is at least 3. So what can we say about the nodes in disrepair? Well, first of all, since every cycle has at least one node in disrepair, if we were to remove all the nodes in disrepair from the graph and their corresponding edges, we would have no more cycles, right? So the graph might be disconnected, but we will have no cycles. So that'll leave a forest of trees as our remaining graph. So in this case, we'd have something like this. So we started with this graph and removed the 3 red nodes and the edges coming off them. So we have this left. So here it's just 2 trees. So why do we like trees? Well, in this case, the edges are constraints, right? But if we have a tree, that makes things easier because we have no cycles of constraints. So if we can just sort of greedily assign values and keep moving between the nodes on the trees, and sort of create a coloring, and we'll never loop back on ourselves with an edge. So we'll never have a constraint between 2 values we've already set, which might cause an issue. So let's pretend the red nodes didn't exist, that we only had these trees in our problem. Well, then what would we do in that case? Like I said, we'd start from some node in the tree and just keep greedily satisfying these constraints, because we'll never reach a cycle that'll cause us any issues. So let's say we'd start here, set this to a 1, set any node to a 1, and now move to the neighboring nodes and satisfy the constraints. So we have a close edge here to the 1. So let's also set this to a 1. Okay. Then we have another close edge, so let's set this to a 1 as well. Now we have a far edge over here. So let's set this to a 5. Let's use the smallest and the largest value that were provided, 1 and 5. We have another close edge here from a 1 to another node, so let's set that to a 1. We have a far edge from a 1, so let's set that to a 5. And we have a close edge from a 5, so let's set that to a 5 as well. So let's do the same thing in the other component. Let's set this to a 1. Again, we've started at a random point. Set this to a 1. Take the neighbor. It's a close edge, so set it to a 1 as well. And then the next node, it's a far edge, so let's set it to a 5. Okay. So we've established that if we just had trees and didn't have these red nodes, and therefore didn't have any cycles, we'd be fine. We'd just do this, and we would never hit any problems. So now we have to we have to bring the red nodes back into the problem, right? We have to bring the nodes in disrepair back into the problem. But what's nice about these nodes in disrepair is the other constraint that we have about them. So if you remember, the first constraint that we've already used is that each cycle in the graph has at least one node in disrepair on it. So if we remove the cycles, we'll just be left with trees. But the second constraint that we have, we've summarized as the distance between every pair of nodes in disrepair. So the distance between each pair of red nodes is at least 3. So if we come back to this graph and reintroduce the red nodes, what does that mean? That means that, first of all, you'll never have 2 red nodes connected by an edge, so that's fine. But also, importantly, that no one node in one of these trees will have 2 red nodes connected to it. So we will never have something like this. This will not happen. And that's nice, because what that lets us do is set all the red nodes to the same value. And we'll say why that's good in a second. So in this, let's just choose 3. Let's set all the red nodes to 3. So why did we need this constraint? Well, if we had something like this, where we have a node and it has a purple edge to one red node and a black edge to another red node, then we couldn't set all the red nodes to the same value, because whatever value we'd set here would have to be both far from and close to that value. So the fact that this cannot happen helps us out. And also it means that we will never have 2 red nodes with a far edge between them. So since we'd never have 2 red nodes with a far edge between them, or 2 red nodes with different edges connected to the same third node, this means we can set all the red nodes to the same value. So let's set all the red nodes to 3s. So now let's look at which edges are satisfied and which edges are not satisfied yet. So all the edges inside the tree, inside each tree, are obviously satisfied, because that's what we just did with all these values. But all the edges that I've drawn dashed at the moment are not satisfied. So how do we satisfy them? Well, the dashed edges are all between 3s and other values, right? So some of these edges are far edges, some of these edges are close edges. So what we can actually do here is we can do something very simple. We can leave the far edges as they are, because actually, if you look here, for example, this 3 and this 1 down here have a far edge between them, and that's satisfied because 3 is far from 1. So this edge is fine, so is the edge between the 3 and the 5. So because we've only used 1s and 5s, all the far edges from 3s are actually satisfied. So we only need to satisfy the near edges from 3s. And that's actually quite easy to fix. If we have a near edge from a 3 to a 1 that needs to be satisfied, we just change that 1 to a 2. and now it is satisfied. So again, over here, we have a near edge from a 3 to a 1, so we change the 1 to a 2. And now this edge is satisfied. If we have a near edge from a 3 to a 5, we change that 5 to a 4. You guessed it. And again here, we have a near edge from a 3 to a 5, so we change that 5 to a 4. So for far edges from 3s to other nodes, we leave the values where they are, and for near edges, we bring those values one closer to a 3. And this works. Why does this work? Well, how do we show that this won't break anything? This won't ruin any of the edges that we already have. Well, let's say we change this 1 to a 2 to satisfy this edge. First of all, we know that this node will not be connected. The node we just changed will not be connected to another red node. So that's not an issue. So that means we only have edges to other black nodes to worry about. So if it was, so edges within the original tree, that means edges within the original tree that it was in. So if it was close to another node in the original tree, it'll stay close because that node will have either a 1 or a 2, and this node has now changed to a 2, so it'll still stay close to that. And similarly, if it was far from another node, so let's say take this edge, that other node will have either a 4 or a 5, it'll still stay greater than 3, and this node will have a 2 now, but that's still less than 3, so it'll still be far from it. So that's the solution. It requires a few key observations. The first one being that all of these constraints that we're given for nodes in disrepair, for these red nodes, are actually useful and applying them the right way. And I think the solution is quite neat because it involves taking two different constraints we have in a graph and satisfying them both with the same set of values. So in this case, I'm referring to the constraints within the tree that we had. So these constraints that we had within each tree, ignoring all the red nodes, and then layering the second set of constraints, which are the near or far constraints to 3s, layering those on top and satisfying both those sets of constraints with the same set of values by alternating between these 4 values, 1, 2, 4, and 5. And how are we doing that? So we're moving between this group and this group. So we're moving between less than 3 and greater than 3 to satisfy these tree edges, the edges in each tree. And then once we've done that, we set the specific value within each group based on whether or not we want to be close to 3. So we pull the ones that we want to be close to 3 into 2 and 4, and that still leaves the constraints within the tree satisfied because 1 and 2 are still close to each other, 1 and 1 are still close to each other, 4 and 5 are still close to each other, 1 and 4 are still far from each other, 2 and 4 are still far from each other, so on. But now we have 2 close to 3, 4 close to 3, but these 2 far from 3. So that is the solution here to interference. I'm not aware if there's any other solutions, but this one seems to be the one that everyone that I've heard has gone for. So I can show you my code for this solution as well. I'll also put it in the description in case you want to take a look. So here's the code. Let's ignore this top part. So the F is the frequencies, which is the term used in the question to refer to the values that we're writing on the nodes. So the final answer will be in this vector. So we go through all the nodes, set the ones to disrepair to 3. Now we have 2 DFS functions. So we run two DFSs in each tree, one called DFS setup, the other called DFS correct. So the first one sets all the values in the tree to 1s and 2s based on whether they should be close to or far from 3. And the second one then corrects that by changing some of the 1s to 5s and changing some of the 2s to 4s so that the constraints within the tree are satisfied, the edges within the tree. So the first DFS sets all the nodes to 1 except the ones that should be close to values with 3s written on them, so nodes in disrepair. And then the second one flips some of the subtrees, setting them to 6 minus the value instead of the value. And this flipping is cumulative. So if you had only one far edge on the path from you to the start of the DFS, then your value should be flipped, where flipping means 6 minus your value will be assigned to your value. If you had two of those edges, then your value shouldn't be flipped. So it's based on the parity of the number of edges, the number of far edges that we've seen on our path from the start of the DFS. So what's important is that we start the DFS, both the DFSs at the same point in each tree. So yeah, that's how this solution works. So that's the solution. This constraint here that the output should always be between 1 and 5, the values you write on the nodes should be between 1 and 5, actually helps more than making the problem harder. At first glance, it feels like it's just another constraint that makes the problem harder, but this constraint actually makes it easier by showing you that all the values you need are just between 1 and 5. So that's the problem. That's interference. I liked the problem. I think it was pretty cool. I actually, fun fact, gave feedback on these problems before the competition. So I solved them beforehand. Yeah, I think it was a nice one. Probably the easiest problem in the problem set based on opinions and also number of solves during contest. So yeah, check out the description for solutions to the other problems if they've already been uploaded. And I'll see you in the next one.